Good afternoon, ladies and gentlemen. In this short video, I'll be preparing for practice B, as in boy, in chapter 19. Before I read those problems, I want to draw your attention to your textbook on page 690, because this section has to do with the magnetic force on a current carrying conductor. So we have a conductor that's carrying current, which is going to create a magnetic force or magnetic field, which then has a magnetic force. So in this picture here, this gray rod represents a conductor, let's say copper wire, even though it's gray. And the current, you see I, we know I is how we represent current. The current is represented going up, in the up direction in this particular conductor, piece of wire. Shows here to the left is the magnetic force. So there's an actual force pushing towards the left. And then you can see these X's. These X's means that the magnetic field is actually pointing down, like from the top of this book, below the book, down my table, down towards the floor. The X means it's going down. Okay, the dot means it's coming up. All right, so it depends on the length of the conductor how much force it's going to be. And the formula here is F magnetic, or the magnitude of the magnetic force, is equal to B, the magnitude of the magnetic field, and hopefully you remember that's Tesla, times I, which is current, which is amps or amperes, times the length of the conductor within the magnetic field. Okay, so that's our simple formula that we're going to need in this section. So let's take a look at the problem. And I'll make sure you can see this. Okay, here's the problem. And this is on page 696, number 32. A wire carries a 10.0 amp current at an angle 90 degrees. 90 degrees. Oh yeah, that's because of the sign. There's really a sign in there that they neglected. But sine of 90 is 1, okay, from the direction of the magnetic field. So it's 90 degrees the magnetic field, 90 degrees to the direction of the current. If the magnitude of the magnetic force on the 5 meter length of wire is 15 newtons, what is the strength of a magnetic field? Okay, so the trick to any of these is just translating. Did I get all the information that they gave me? So here's your translation. All right, they told me that the current is 10 amps and it's 90 degrees from my magnetic field. The force is 15 newtons, and we know that the length is 5 meters. So what is the strength of the magnetic field? How much Tesla is it? And so as we just saw in the book, the equation of the magnetic force, yeah, the whole word magnetic there, is just B-I-L. Okay, so we know the magnetic force, we know the current, we know the length, and the question is, what's B? So now you guys are really good at reducing it to the variable that you want to solve for. So I want to solve for B, so clearly I need to divide both sides by I times L. So my I's cancel out, my L's cancel out. So then I have B, my magnetic field strength in Tesla, is equal to the magnetic force is newtons, divided by the current times the length. Okay, straightforward. I've got 15 newtons in the numerator times the current, the current, which was 10 amps, 10 amps, and the length, which is 5 meters, 5 meters. All right, so I have 15 divided by 50. 15 divided by 50, I know that 15, I just don't know. 15 divided by 50, it would be like almost a third maybe? Let's see here. 15 divided by 50. There it is, 0.3. So it's 0.3, and what am I looking for? B, so that would be Tesla. All right, so really, because of all the significant figures here, we have 3. I got to do 3 significant figures here. There we go. So 0.3 Tesla is the magnetic field. And all I needed was the original formula, which is BIL. BIL. This is not one that I have memorized. I didn't use it that much. All right, let's look at number 33. Number 33. There it is. A thin 1 meter long copper rod. Oh, they already told us the length, and they're telling us it's copper because we know copper is a really good conductor. In a uniform magnetic field has a mass of 50 grams. Okay, so we're given a length, so we're given a mass. When the rod carries a current of 0.245 amps, so that's the current, it floats in the magnetic field. What is the field strength of the magnetic field? So just like before, we want to know what the strength of the magnetic field is. So we want to know how many Tesla. So let's see, how did I translate this problem? It's over. There we go. Here's how I rewrote it. They gave me the length. They gave me the mass. They gave me the current, and they gave me the B. First thing I would write then after all that is the equation that's probably going to help me. The magnetic force is equal to the magnetic field times the current times the length. All right, so I notice that I want to get B. So just like before, B is going to be the magnetic force divided by the current and the L. So I have the length and I have the current, but I don't know what the magnetic force is. But interestingly enough, they gave me the mass. So if I have an object, there it is, of a certain length, but it has a mass, I know that there's a force going down. There's a gravitational force. So that's all I have. I have a gravitational force. So that must be what it is. Because of its mass, there's a force pushing down. So what is that? Well, I know it's mg. They gave it to me in grams, which I don't want. I always want kilograms so that I can have this in newtons. So hopefully by now you know that kilograms, there's 1,000 grams in a kilogram. So you can convert it. I happen to know that I just have to move it over 3 decimal places to the left. So that would be 0.0500 kilograms, right? So if I were multiplied by 1,000, that would give me 50 grams. Okay, so that would be my M. That'd be 0.05 kilograms, and your good friend, acceleration due to gravity, 9.81 meters per second squared. And that would give me Fg. So that's the only force that I have. Let's see what that is here. 0.05 times 9.81. 0.4905 newtons, and I'm going to leave that in there, 0.4905 newtons. So that's what I'm going to use for the force, because it's the only force that I have. It's got to be able to have that, at least that much force. Okay, so I'm going to plug that in here. So I've got 0.4905 newtons, and my current was 0.245 amps. And my length is 1 meter. There we go. So all I have to do is take that and divide that by 0.245. So I don't have to multiply it by 1. It's the same thing, 245. And I get 2.00, let's see, 2.0020408. And this would be Tesla. So I do need to look at my significant figures. There's 3 here, 3 here, 3 here. So I'm going to go with 3. So I'm going to have exactly 2.00 Tesla. So that's going to be the strength of the magnetic field. And again, everything just goes back to the equation. The magnetic force is the field strength. So this one's in Tesla. And current is in amps, and length has to be in, that's an A, it would have to be in meters. Those would be the units. And that's it. So we did both 32 and 33. Okay, so that's it. So I will see you next time.